The phase diagram of the lithium hydride system.
The phase diagram of the lithium hydride system is complex. These studies have identified several systematic features in the phase diagram of the lithium hydride system.
So in our discussion, we are going to tackle about the phase diagram of the lithium hydride, the behavior of its isotherm, and its monotactic properties.
Let's now proceed to the phase diagram of the lithium hydride system. So in this diagram, we will have the temperature in the y-axis and the mole fraction of the lithium hydride in the condensed phase on the x-axis. And you can see in this part of the graph, the alpha phase, which is the lithium enriched phase, is arbitrarily distinguished in the beta phase, which is the lithium hydride enriched phase. The S and L subscripts denotes the state of the lithium and the lithium hydride. So in this part of the graph, we can see solid and the liquid phase of the lithium. While in this part of the graph, we can see the liquid and the solid phase of the beta or the lithium hydride enriched phase. So while in this part of the diagram, the liquid alpha phase or the lithium is added to the beta phase in the solid phase. This line in the graph shows the eutectic line, and the point C is the eutectic point where the temperature of the mixture of melts or freezes. So, and points A, C, D, F, and H is the solidification line where we can see the alpha phase and the beta phase in solid phase. So D and F and G is the monotactic line, and the temperature slightly above the monotactic line shows the vapor and the liquid phase are in equilibrium, while slightly below the monotactic line, the solid, liquid, and the vapor phase are in equilibrium. Now, points D, F, and K shows the immiscibility zone of the phase diagram of the lithium and lithium hydride. In the immiscibility zone, lithium and lithium hydride coexist with each other in equilibrium and does not mix with each other. So let's look further in this region. This figure shows the pressure and the composition phase diagram of the lithium hydride system. So as the pressure increases and reaches the immiscibility zone, the pressure remains constant at these lines. So outside the immiscibility zone, the pressure approaches infinity while X reaches to 1. When P approaches infinity and X is equal to 1, means that the lithium hydride stoichiometric composition cannot be attained hypothetically. This isotherm behavior does not only apply to the lithium hydride system, but it also applies to many systems containing the metal hydrides.
Now, let us discuss the interesting property of lithium hydride. So the figure here shows the diagram of pressure composition of the lithium hydride system above the monotactic line. So the four curves here are the different system of lithium hydride subjected to different temperature. So as we analyze this graph, once the composition of lithium hydride increases, the pressure also increases. But in the dissociation of lithium hydride, it produces lithium and hydrogen gas. So the only pressure here indicated is the pressure or the vapor pressure of the hydrogen gas. So the interesting part of this graph is even though the composition of lithium hydride increases, the pressure of the hydrogen gas is remaining constant inside this immiscibility curve, which is the dashed lines here in the graph. But outside the immiscibility curve, the pressure of the hydrogen gas sharply increases up to infinity. So it's really hard to know the stoichiometric composition of lithium to hydrogen gas. So Now let us prove how does this happen. So now let us assume of a closed system in which lithium hydroxide is evaporated. So if there is no reaction involved, the vapor pressure of lithium hydride is also equal to its saturation pressure. But actually, there is a reaction involved, which is the dissociation of lithium hydride into lithium and hydrogen gas, shown in this reaction. So lithium hydride is an irreversible reaction which produces lithium and hydrogen gas. So once the evaporation happens, the molecules of lithium hydride decreases. Hence, the vapor pressure of lithium hydride also decreases. But at the same stage, the vapor pressure of lithium is still greater than its saturation pressure, assuming that all lithium is still in vapor phase. So as a definition, saturation pressure is the pressure in which from liquid to gas is equal to gas to liquid. So meaning the molecules going out of the liquid stage is equal to the molecules of the gaseous state going back to the liquid state. So since we are dealing with a closed system, all the vapor or the gaseous form of lithium must condense back to liquid form. So if there were no mixing of lithium with lithium hydride, a new portion of lithium hydride must be vaporized in order to restore the initial vapor pressure of lithium hydride, which only be true since we are dealing with constant temperature. So the evaporation and decomposition would evidently continue until all condensed lithium hydride would now be turned into vapor, and what's remaining in liquid phase is the lithium or the pure lithium. But this situation does not exist since pure condensed lithium hydride could not coexist with pure vapor of lithium hydride. It only exists if before the dissociation of lithium hydride, lithium is first dissolved in lithium hydride. So since a solution of lithium in lithium hydride forms in the liquid phase, the partial pressure of lithium is proportional to the concentration of lithium in the liquid phase if the liquid is in phase equilibrium with the vapor. So here, P or the saturation pressure of the lithium is equal to the vapor pressure of the lithium times its activation coefficient times 1 minus x, where x is the composition or the mole fraction of lithium hydride. Since we are dealing with equilibrium and also dissociation, so what we need to have is the equilibrium constant of the dissociation of lithium hydride. So from our equation, the dissociation of lithium hydride, so PLi is the pressure of lithium, while times the pressure of the H2 raised to 1/2, since the coefficient of hydrogen gas is 1/2, divided by the pressure of lithium hydride. So from the equation of the saturation pressure of lithium hydride, once x approaches to 1, or once the composition of lithium hydride increases, the pressure of lithium approaches 0. So in the complete dissociation of lithium hydride, so the pressure of lithium hydride would approach now to 0. So what happens to the pressure of hydrogen gas once the pressure of lithium hydride approaches 0? So now the pressure of hydrogen gas would now lead to infinity. That is why outside the immiscibility curve of the pressure of the hydrogen gas, it sharply increases up to infinity.